Okay, I want to look at a topic called continuity of a function. We're going to look at where a function is what we call continuous. Continuity of a function. You may have seen the term continuous in an algebra class or something like that, and it's usually described very vaguely, such things as like there's no breaks in the graph or something like that. So we're going to define it precisely here and investigate some things with it. So let's define what continuous means first. So we say a function, let's call it f, is continuous at a. So a is an x value. Anytime you talk about where on a function or when on a function, that's an x value. So since we're saying at, this will be an x value. So a function is continuous at a if the following condition is true. If the limit as x approaches that a value from both sides of the function f of x, if that equals f of a, in other words, if the limit of the function equals the output of the function, we say the function's continuous at a. Okay? So some things to think about when we're trying to decide if this equation is true. Well, really two things have to happen before we can decide if they're equal. If the limit doesn't exist, then this statement can't be true. If the function doesn't have an output, this function can't be true. So it's important to understand that both of these have to exist before we can investigate whether they're equal. So if you can ever decide that the limit doesn't exist, or that the f of a doesn't exist, or the function doesn't have an output, same thing, then you can conclude that the function is not continuous at that value. Okay? So let's look at some examples with graphs first. Let's do a visual inspection of this condition. So the first function we might look at, let's say, maybe it's just like a polynomial type of function, right? So maybe something like this. You notice it's a nice smooth curve. There's no breaks or gaps in the function. And so we can investigate a particular a value. So let's say we want to investigate where a equals, let's call this a value 3. Okay? And we can see that when a is 3, we're dealing with this part of the graph right here. So if we consider the limit as x approaches that a value of 3 of the function, let's call this function f, of the function f of x, we can see that this limit exists because as we approach 3 from both sides, we're converging to this y value, whatever it is. So let's label this y value as, we'll use a different scale here. Let's say this is 2. So as x approaches 3 from both sides of this function, we get a y value of 2. So that's the first part of this definition. The limit has to exist. It does. It's 2. Then we have to look at, okay, so as we approach 3, our y values get close to 2. But the other part is, does the function actually output 2 for the input of 3? So if we look at this, what is f of 3? So we go to 3 on the x-axis, and its output is actually 2. And so because these are equal, we can say that f is continuous at 3. Okay? So it's that simple. And basically on a graph, when you don't have gaps or breaks in your graph, the function will be continuous. So you can see that at this x value, at this x value, at this x value, every x value on this graph, this function is continuous. Okay? So pretty straightforward there. Let's look at a more interesting example. Let's consider a function that looks like this. We'll call this function g. Let's say that this function looks like an absolute value type of function, this v shape, but at the vertex of the v we have an open circle. So it looks like this. And let's say that open circle occurs at the x value of 2. Okay? And you can already see that this function is continuous at all the other x values besides 2. That's easy to see just for the same reason we talked about with the polynomial. Okay? The question is the function continuous here? So what we do is we look at this and we have to see, okay, first of all, does the limit exist? Well, the two-sided limit does exist for sure because both are converging to the same y value. Let's say that y value is 4 in this case. So the two-sided limit is 4. I'm not going to write that down because now does f of 2 exist? And we can see in this function that, g of 2, let's say. I named the function g to my demise, of course. If we look at g of 2, we're asking what's the output of this g function at 2. And since this is an open circle, g of 2 does not exist. That's an e, by the way. G of 2 does not exist. So what we conclude then, we could say therefore, these 3 dots in the triangular configuration mean therefore g is not continuous at 2 because there's no way that the output and the limit can be equal if the output doesn't exist. So therefore g is what we say discontinuous at 2. So that's one example where a function is not continuous. And you can see the graph has a gap in it, a break in it, okay, at that value. Let's look at another example. So I could have reused that graph. Let me come up with something slightly different. Let's say we have this sort of piecewise defined function that is a horizontal line until it reaches the x value of 1. And when it reaches that point, it terminates with a closed circle. Let's say it goes to the left forever. It's a horizontal line. And let's say this y value is 2. And then after 1, it picks back up with a different function, maybe that is a straight line again, starts with an open circle and goes off diagonally in that direction. And let's say that this y value is 4. Okay? So now we have to investigate, is it continuous at 1? Maybe you suspect that it's not because there's a gap in the graph. There's a break there. And we have to convince ourselves using the definition of continuity. So we have to decide, does the limit exist? Does the output exist? And are they equal? That's what we're looking for. And so we can see here that f of 1 does exist. If 1 is your input, we have an output on this function. So f of 1 exists. Okay, so that's not a problem. Now what we want to do maybe, though, is look at the limit as x approaches 1 of, let's call, I used f, so let's use f of x. So now as we approach 1 from both sides, the right-sided limit is going to 4, while the left-sided limit is going to 2. So this two-sided limit does not exist. Well, if the two-sided limit doesn't exist, there's no way that statement can be true, right? So therefore, f is discontinuous at 1. All right, let's do one more example with a graph. And we want to see an example of a function that's discontinuous, but both of those values exist. So let's say we have a similar piecewise defined function that again is a horizontal line until it reaches 1. Then we have an open circle. And then the graph picks up with another piece that goes diagonally off like this again. Except this time the two pieces connect at this open circle. Okay? So we can see that the two-sided limit, let's label this y value now. Let's say this y value is 3. We can see that the two-sided limit as x approaches 1 of, let's call this g, of g of x, the two-sided limit is the y value 3. And currently, g of 1 g of 1 does not exist. We've already seen a case like that, so I'm going to make a change here, and I want g of 1 to exist now, but I don't want the function to be continuous. So if I wanted the function to be continuous, I'd have to close this circle so that the output at 1 had to equal 3, just like the limit equals 3. So what I'm going to do now is give 1 an output that's not right here. So let's say that the output of 1 is way up here. And let's call this y value 6. So now we can see that with this definition of the function g, g of 1 equals 6. So now both of the values exist, but because they're not equal, we can say that g is discontinuous at 1 again. So lots of things can make your function discontinuous. Either of those values don't exist, or they both exist and are not equal. Okay? All right, let's look at some algebraic examples now. And we should have the definition down, so I'll erase that so I have more space. Let's determine if f of x equals, determine if f of x equals 1 over x is continuous at 3. Okay? Determine if that's continuous at 3. Well, so how do we do that? We look at the limit as x approaches 3 of f of x. And we want to know if that equals, does that equal the output of f at 3? Is that true? So let's evaluate both of these. So the limit as x goes to 3 of f of x, well, that's the limit as x goes to 3 of 1 over x, which we can evaluate this limit by direct substitution, so that's just 1/3. We want to know, does that equal f of 3? Well, f of 3 means plug 3 in for x, and we get 1/3. So all I'm doing is working down on each side of these. And we can see that 1/3 does equal 1/3. Therefore, f is continuous at 3. Okay? So that's a pretty straightforward example. And basically, whenever you say the limit equals the output, that's telling you that if you want to know the limit, you can just do direct substitution. You can plug 3 in for x and calculate the limit. That's only true for continuous functions. All right, let's do another example. Let's look at a piecewise defined function. Let's say f of x equals, the first formula is x plus 1, and we'll say that it's x plus 1 if x is greater than or equal to 2. And then the next formula, let's say, is 2x minus 1, and let's say that's if x is less than 2. Okay? So determine if f of x is continuous at, I bet you can guess the x value we're going to look at. If we looked at x values less than 2, well, we know this function is going to be continuous because we can evaluate the limit of this function by direct substitution. If x is bigger than 2, we know this guy is continuous because we can find its limit by direct substitution. So the interesting thing is, what about at 2? Because to the right of 2, we have one output. To the left of 2, we have a different output. So let's see how this works out. So what we have is we need to look at the limit as x approaches 2 of f of x. Okay? But because f of x is defined differently to the left and to the right of 2, we have to look at the left-sided limit and the right-sided limit. So let's look at the left-sided limit first. If I'm looking to the left of 2, I have to use this formula to calculate my outputs. So I'm taking the limit as x approaches 2 from the left of 2x minus 1. And I can find that limit by doing direct substitution. Plug 2 in for x, and I get 4 minus 1, which is 3. Okay? Then I need to look at the right-sided limit. And whenever x is bigger than 2, I use this output formula. So I've got the limit as x approaches 2 from the right of the output formula x plus 1. And again, I can do this limit by direct substitution, and I get 2 plus 1, which is also 3. So because of this, I know that the limit as x approaches 2 from both sides of f of x equals 3. So we're currently on track to prove that this function is continuous at 2 because at least the limit exists. So that's key. The limit exists. Now what's the other part? There has to be more to it than that. Well, the other part is a little bit easier. We have to look at f of 2, right? So what is the actual output of this function when x equals 2? Well, when x equals 2, we have to use this output formula. And so I have to plug 2 in, so I get 2 plus 1, which equals 3. All right? So what can we conclude? Well, since the limit as x approaches 2 from both sides equals 3, and that equals f of 2. So this is a common thing in mathematics. I wrote the limit as x approaches 2 of f of x equals 3, which also equals f of 2. So clearly, the limit as x approaches 2 equals f of 2 because all of these are equal. So since the limit equals the output, f is continuous at 2. Okay? So the nice thing about the two pieces of the function is they actually meet together when x equals 2. If they don't come together to the same point, the function couldn't be continuous because the limits would not match each other, and so the limit wouldn't even exist. So there are some graphical examples of continuity of a function, some algebraic examples. I can't do all the cases, but hopefully with your algebra skills, your graphing skills, you should be able to apply this definition of continuity to a variety of different functions.